to process 2D crystal images in a single processing style. And the second is to use a maximum likelihood algorithm. So today my talk is to just answer the questions why we need these two techniques. So if we have perfect crystallography method works very well and it is very effective, and I think it should be the first option. But if we have crystals that has small deviations from the perfected crystal, then the crystallography method handle the problem through Fourier filtering and unbanding. I think Marcel introduced unbanding yesterday, and we have some concerns regarding the unbanding. The first things we ask the questions how actually unbanding is conducted. So we know that we shift the small patches, so to artificially make a perfect crystalline. So through this procedure, I think theoretically we should introduce some sort of distortion. I think there's some either gap between the patches or overlap. But it's just because the resolution, our resolution is not that high so that we can notice or we care about the distortion, or we don't have any exact answer how to overcome those problems. So the more important thing is that unbanding basically is in two-dimensional space. So here I would say that even though we only use translation, the shifting, but because we shifted small patches, so somehow the rotation can be roughly achieved because we shift the small patches, right? So somehow we can achieve some sort of rotation, but it's very rough. So no matter what, the data basically is manipulated in two-dimensional space. So there's no way that we can extend the unbanding to right now. No way to extend the unbanding to 3D space. So that's the main concern for the crystallography method, in my opinion. So based on these kind of observations, people have tried to use a single particle method to process 2D crystal images, and they have published the work before. And the idea is to just using a single particle processing method to process the patches extracted from the 2D crystal images. So we know that in single particle area, it's very common that we use cross correlation. Not only in single particle, actually here in crystallography method also we use cross correlation, right, to locate the unit cells. So we know the cross correlation idea is to try to find the best translation, and alpha we consider the in-plane rotation. This is for two-dimensional space. So to try to find the translation and the rotation for a specific image xi. So, and then when we align the particles and when put them together, we try to find a reconstruction of the image. So now here I just want to show some of the tricky things in cross correlation based alignment. It is highly dependent on the reference that Henry mentioned before. It's dangerous if we use if we use the reference in an appropriate way, or we have have some problems. And I also, I hope that in the end of the talk, I will show you how we get something that we can never imagine from the pure noise. Okay, so here, let's say, if we have the excellent reference, because the idea of the cross-correlation based alignment is that we use a reference to try to align the images or the particles. So if we have the perfect reference, let's say we assume here is the object or the image. So we have the object is shifted a little bit by 10 pixel, and if we have this one to do the cross correlation, no problem. We have a cross correlation map, and easily we can tell the peak is at a 10 because this peak indicates the translation. And even though with a pretty strong noise, but if we have perfect reference, we still can find the peak at 10, even though the map is noisy, but we can find the peak easily. But this is in the case we have the reference that is just the answer, but this is impossible because we are trying to look for the what? We are trying to look for the object. So now if we don't know the object and not object, we don't know the reconstruction, then we try to get it through alignment. That means we are using something that's different from the real. I would say the real structure, different from the real structure. And then, for example, this is very common. Initially we use some Gaussian image to do the cross correlation and try to find the peaks in the cross correlation map. And here we use a bigger one and we use a smaller one, and then we can see the peak in the cross correlation map. Cross correlation, they are different from the real location, right? Translation. This is a very simple one. There is no rotation. There's no rotation. It's just a translation. So this gives us some hints that if we don't have a good reference, how much we can rely on the result we get from cross correlation. So obviously, the cross correlation of a single image with a reference is not very reliable. It's not very reliable. So when we put when we do the alignment, when we put like 1,000, 10,000, this kind of aligned things together, what is the result? Nobody can control. I think we can hardly to tell. The result, what it is the real thing or not. I think so, because individual image alignment is not reliable due to the reference bills. I think we are trying to look for a solution from a completely different point of view. So here we are. Here is the maximum likelihood approach. In this approach, we are not trying to find out the exact translation and rotation for each individual image. We're not trying to do that. Instead, we consider this as a random number from a specific distribution. So we don't know how much it should be 3 or 4 pixel translation. No, we don't know. We just know that it might be some range with some distribution. Okay, and then we're trying to find the parameters because it's a distribution, so it should have some parameters define the distribution. So we try to find the parameters which can maximize the likelihood of the observations. Let's say if we see a set of data, 3, 4, 5, 6, 7, whatever, so we assume these data are generated by a Gaussian distribution. Our question is that what distribution generates these observations? Is that okay? Yes. So we are trying to look for that. So here, in order to solve the problem, so we need to build a mathematical model for the application. The model is that here, let's see here, we have some, let's say, molecules, and so these molecules, through translation and rotation, we have a pair of images, and in addition to that, we also have noise, as we know. So through this procedure, we ended up with a pair of these images. This is what we have in hand. So our problem now is to, from this observation, we try to figure out what is the original image, or what is the original structure. What is the translation and rotation? What is the distribution of the translation and rotation? What is the noise? For the translation, rotation, and noise, we are talking about the statistics, not the exact number. So the statistics. So here is the image model, image data model. So xi is the image, the particle we have. So this is a result of the structure through translation, rotation phi. We consider translation, rotation phi, and then plus the noise. This is the result. This is the image we have. Okay, so now the likelihood. The idea of maximum likelihood is that we define the likelihood of the observations. So here is it. I think we can first look at here. This is the likelihood, mathematical likelihood. So we basically, if we have let's say 1,000 image, so the likelihood is just defined as the possibility of the first image, the second image, all the images. We assume the images they are independent. So the likelihood of this parameter set is the multiplication of the probability. So here, let's go back. So we want to find the parameters which include the structure A, the translation rotation sigma, and the noise. So this, we want to try to find the parameters that give us the observed particle xi. Observed particles. So for the noise, we assume it's a Gaussian distribution, and the translation and the rotation, actually we can consider it in different ways. Translation, we consider translation, it's also a Gaussian distribution, and the rotation, you can either define it as a uniform distribution or rotation. I think you are more aware of this real situation. This should be real. The model should reflect the real situation in your application. So you see how much likely that how likely that your rotation you have slightly different, or you have the uniform. You have a Gaussian distribution. That means most of them has 0 maybe, or whatever. So the distribution you should define the distribution in a way that is real reflect the application situation. So here's that likelihood, and this is just mathematics. So the likelihood the multiplication is not easy to handle, so we change the multiplication to logarithm, so it becomes a summation and this. So now the whole idea is that we define a likelihood function, and in this function we have the parameters in the mathematical functions. Now, from our mathematics knowledge, we know that if we try to maximize a function, and what we should do is to do, differential, right? The differential to find. So see here. This is a function. This is a function, and this function is a function of some, variable. Which we try to find the maximum value of this function. We need to do what? Differential. Try and look for the points that the differential is zero, which should give us the maximum value. So that's the idea. So because we have the structure, the noise, and the translation rotation, so we just do the partial differential with each parameter, and then we set it to 0. And then we get the formula or the equation that we can use to update the parameter. So as a result, because that means we can do the partial differential equation to the structure, to the noise, and to the translation, and to the rotation. Here I just give my example, the partial differential to the structure. You can do the same thing. So as a result, we just look at the result. So as a result, here the structure will be from the, you see here is a sigma, is a summation, and summation we have integration here. So we see here, each particle xi contributes to the final structure in multiple ways. Here is the weight. Gamma is the weight. You can see here is the weight, and the weight we have seen here. The weight is here. It's defined like this one. It's defined using this equation 5. Anyway, so we consider all the possible rotation. Phi, we know that phi is the rotation and the translation. So all the possible rotation and the translation, we consider it, and we apply to each individual particles. So the idea, so if we compare this with the cross correlation, then we can see here the cross correlation. The structure is from the particles, and each particle contributes to the structure in a specific translation and rotation, right? Translation and rotation. And this specific translation is phi I, it is defined for the maximum correlation. Compare this one, if we look at the maximum likelihood, here we say that xi, we do the integration in all the possible rotation and the translation. But just each rotation and the translation has different weight. That's the result. And so this is the maximum likelihood, and implement it in the program. We implement it using expectation maximization. We call it EM algorithm. This is an iterative algorithm normally used to implement the maximum likelihood. So now we have the simple algorithms here. So we set initial parameters. We know we have this initial parameter A, and the structure, and the noise sigma, and the translation rotation. We just set random, and then we repeat. So the first step, step 3, is called expectation. Expectation means we calculate the weight, gamma. We calculate gamma here. That's the gamma. We calculate the gamma. Yeah, that's the expectation. And then we use the equation 6, the previous slide, to do the maximization, because this procedure is this update is from the what? Maximization, right? So let's call it expectation maximization. So here is the expectation. We calculate the expectation, the probability, and then through the maximization, we get the updated value for the parameters. This is the steps. It's pretty. Now, if I did some simulation experiments on single particles. On single particles, let's say if we have a structure, this kind of structure, and I just simulated using the translation and the rotation, and we generate some like several thousand particles, and this is some sample shown here, and then we add noise. Of course, here we didn't consider about the CTF. We didn't simulate CTF. I didn't simulate the CTF. Just put the Gaussian noise here. So so these are the images that with translation, rotation, and noise that we have. And then we use an initial reference. By the way, here the initial reference can be anything. You can take anyone, random pick up anyone, or you can just even use a pure noise. Using pure noise, because I would say the biggest advantage of maximum likelihood is it is, I mean, not absolutely, but I would say it's reference free. It does not depend on the reference. So when we do the maximum likelihood, this is the initial first reference, the initial reference, and when this is the iteration 1, let's say iteration 2, or several. After several iterations we have here, we see now the search. In terms of the search, we do the search by step 2 degree, and the images here. In the first experiment, I just did 2 experiments. The angle is, from 0 to 30 degrees. We randomly rotate the structure. So we search by step 2. You can search by step 1, but it's going to be slower. And here's the result we get. And in the second experiment, we rotate the angle using like 72 degrees more. That means, the angle range is bigger, and then we do the search. The search is 6 degrees. We search is 6 degrees, and still start with any random initial reference. We get the result. So this is an ideal situation because the rotation and the translation we control. In the simulation, we control it because the numbers are generated from a real Gaussian distribution function. So the noise is also Gaussian. So now the next thing is we want to apply this. By the way, it's maximum likelihood. We are not the first proposal to use it. It has been used in the single particle processing. And now we apply this algorithm to 2D crystals. So in the case of 2D crystal images, I think we have more advantages because crystals, it does not have that big range for the. It's not like real single particle. It's still we have limited distortion, right? Limited rotation angle. So the search range will be small. That's very important for maximum likelihood because the algorithm itself, it is pretty slow. The larger the search range, the complexity of the computation will be exponentially increased. So now we have, that means we have relatively manageable statistics of the translation and the rotation. So the data here, I would say that here the maximum likelihood is a refinement procedure. So we should use it. After we process the data using 2D other algorithm. Conventional crystallography algorithm. The purpose is just that we can locate in the pre-processing. We can approximately locate the particles, okay, the particles, so that we can extract, we can crop the particles from the two-dimensional space, and we can also get the tilt geometry from crystallography method, because that means we just need to adjust in a small range to refine the parameters, but we already have approximate idea. Okay. So now, because this is a real, in the case of a real application, we have to consider about the CTF issue or whatever. So now in the maximum likelihood, in the mathematical model itself, we assume the noise is, we call it independent noise. Independent, that's why, because of it is independent, then we can get the compilation, the probability of the compilation by using multiplication of individual probability, because they are independent. Otherwise, we cannot do that. So in order to achieve this, I mean, to satisfy the requirement, we need to do, we call the whitening. So here we use a whitening filter to initially to process the 2D crystal image. And this is a flow chart. So let's get a basic idea. So here is the raw image to the crystals. We process the image using the conventional crystallography method. We get the profile. So we know that in the profile we have the approximate unit cell coordinates, and we also have the tilt geometry. And then here there are two, lines. So this part basically is for the maximum likelihood. This part is for maximum likelihood because we need to apply the whitening. The whitening is just because of the requirement of maximum likelihood. It's not the requirement of the crystallography processing. So apply the whitening, and then we get the final result of the whitening is we get the weight or the gamma. We would see the gamma, we get the weight. And then here in this line, we mainly try to correct the CTF, the CTF. We know the CTF, and so the CTF in my program, I take a conservative way that I only mainly correct the phase. Corrected phase. It is conservative, but I think it is safer. It's safer to correct the phase, and so once we get the weight or the gamma from the maximum likelihood algorithm, then we can apply this weight to all the to the particles and get a final map. So that's an example. We had it. And this is bacterial dot sum. So this is the initial reference we used, and it's through several steps, and we get the final, the final projection map. And here is the crystallography method. I will see. The structure from maximum likelihood. Generally, when you have very good crystals, it should have very similar result. But if you have bad crystals, this method should be better. You should see better result than crystallography method. That's, now the last two slides I want to talk about is not it's just my observation, and I just give you the idea of what I'm thinking about. So increase the number of images. Increase the numbers. People usually say, okay, we should add more images. So we can expect a better result. Now, so if you have, for example, images with noise ratio, like, let's say here, image data 1 and image data 2. Image data 1 has half signal noise ratio of the image data 2. So if we double or even triple the number of the particles in image data set 1, can we expect the same result from the two data sets? No, because I mean, when we have noise, and that's here, which I showed the result is that's when I'm saying that I did some simulation experiments. So that means, I mean, noises can be reduced somehow by increasing the number of images, but not necessarily as much as we think. So, for example, this also shows us how. So, in this experiment, we have like 2,000 pure noise images. Let's say we have pure noise images. There's no underlying structure in the image, and then we choose some reference and try to do the initial to do the alignment using maximum likelihood and cross correlation. And here I show you here the B and C. This is the initial. After one alignment, one time of the alignment, we get B from maximum likelihood. We get C from cross correlation. And after 100 iterations, this is the result we get from maximum likelihood. This is the result we get from cross correlation. I think this is not new. Before Nico, yes, he did the experiment using Einstein's picture, right? Using Einstein's picture and the noise data set. He was able to, he said, okay, if we use Einstein's picture to align the noise, we ended up with what? Einstein's picture. Because cross-correlation, the idea is try to look for the reference in the image. So you can always, I mean, ended up with something that's I mean, basically tend to be close to the reference. So here's 2,000 pure noise images, and now if we increase the image with 10,000, so if I use 10,000 pure noise images, let's see here. So we repeat the same procedure. This is the first iteration, and after 100, this is the maximum likelihood. This is the cross correlation. So that means, I mean, if the noise dominates the images, increasing the number of images does not help that much. So because we always get some correlation. From the mathematics calculation. So this is what I just, because normally people, I mean, we tend to say we use more images, then we can get a better result. As well as here, we have to consider the real structure. The real structure is unknown. So we can never expect something that, I mean, the reference is the real structure, right? So in that case, I mean, the noise images. I mean, I just did this example, and I think about, okay, so this work was done in our group, and Starbuck Lab at UCLA's. Of course, Henny is the PR here, and he co-constantly started. Yes, I hope for this. I am still new to this electron microscope Scarpe community. And I just want to say if I can contribute a little bit, I introduce different ideas from people with different backgrounds, so that we can make you have more, we have more diversified ideas.